Hi friends, in this video we are going to discuss about previous gate questions in our DC machines. Let's see the first question. One, see here, a separately excited DC motor. This is a separately excited DC motor. Has an armature resistance of 0.5 ohms. It runs from 250 volts DC supply, drawing an armature current of 20 amperes at 1500 rpm speed. What they given? They given armature resistance 0.5 ohms and armature current 20 amperes, and they given supply voltage 250 volts. Supply voltage 250 volts, and also they given speed n is equals to 1500 rpm. 1500 rpm. For the same field current, nothing but for the same excitation, the torque developed for an armature current of 10 amperes will be. The torque developed for an armature current of 10 amperes will be. This is our question. Right? So let's see now. First we have to know the formula for torque. What is the torque formula? It's a general formula. Torque T is equals to P by omega. Torque T is equals to P by omega is a common or very general formula. But in our DC machine, P is equals to back EMF into armature current. Back EMF into armature current. And generally, omega is equals to 2 pi n by 60. Omega is equals to 2 pi n by 60. Let's calculate EB. For DC motor, what is EB? EB is equals to V minus IARA. V minus IARA. Let's find it. V they given 250 volts. Minus IA they given 20 amperes. And RA they given 0.5 ohms. So minus IA. What is IA now? 20 amperes into RA 0.5 ohms. 0.5 ohms. Then tell me what is answer? 250 minus 10. 20 into 0.5, 10. 250 minus 10 is nothing but 240 volts. So, I calculated EB value. Let's calculate the torque T. So, T is equals to EB into IA, right? What is EB? 240 volts. Sir, why you are taking 240 volts only? Because here for the same field current. If there is no change in excitation, there is no change in field current. If there is no change in field current, there is no change in back EMF. This is same, but they given the armature current of 10 amperes. Armature current of 10 amperes, EB into IA, divided by 2 pi n by 60. 2 pi n by 60. Nothing but 2 pi into, what is our speed? The given speed 1500 rpm divided by 60. Let's calculate this value. And you can get the answer. Let's try to calculate this value. Yeah, tell me what is answer. After calculation, the answer is 15.2788 Newton meters. This is our answer. The torque developed by the motor is 15.2788 Newton meters. You can get this answer after solving this. Right. What I told you, just they asked me the torque developed by the motor at a given armature current. Torque T is equals to P by omega, where P is equals to EB into IA. Nothing but the back EMF into armature current and omega 2 pi n by 60. EB, I calculated EB for motor, that's why V minus IARA, and its value is 240 volts. Then after torque T is equals to EB into IA. IA they given 10 amperes. EB into IA divided by 2 pi n by 60. After calculation of this one, we can get 15.2788 Newton meters. Okay, next question. Neglecting all the losses, they neglected all the losses. The developed torque, for example, torque T, the developed torque of a separately excited DC motor, the developed torque of a separately excited DC motor operating under constant terminal voltage, operating under constant terminal voltage is related to its power output. Is, for example, my power output is P. For example, torque is T, power output is P, and they given that constant terminal voltage. Constant terminal voltage. Let's tell me what is the relation between them. What is the relation between the developed torque and the power under constant terminal voltage? That is my question. Right, tell me, generally we know that in our DC machine, torque is directly proportional to phi into Ia. Right? Torque is directly proportional to phi into Ia. And they given it is a separately excited. That's why generally the flux is constant in separately excited motor. Here the flux is constant in separately excited motor. So the torque is directly proportional to Ia. It's generally. And they given that the power output. In our DC machine, the power is nothing but EB into Ia. Power is nothing but EB into Ia. And they given that constant terminal voltage. Here they given that the voltage is constant. Voltage constant, nothing but here the back EMF also constant. If back EMF is constant, what is the relation between power and armature current? The power is directly proportional to Ia. The power is directly proportional to Ia. Let's see here once. Here torque is directly proportional to Ia and power is directly proportional to Ia. Then tell me, from these two, what is the relation between torque and the power? Here, torque directly proportional to Ia and power directly proportional to Ia. That's why the power is directly proportional to torque. The power is directly proportional to torque. This is 100% correct answer. Or torque is directly proportional to power. Right? So which of the following is correct answer? Here, the torque is directly proportional to power is 100% correct answer. Right? Just they asked me what is the relation between torque and power for separately excited motor, and they given constant terminal voltage. And generally torque directly proportional to phi into Ia. Here flux constant, nothing but torque directly proportional to Ia. And P is equals to EB into Ia. V constant, nothing but back EMF constant. Right, sir? Now tell me, here power directly proportional to Ia and torque directly proportional to Ia. So the power is directly proportional to torque. The second answer is correct answer. A cumulative compound long shunt motor. Right? They given a cumulative compound long shunt motor. Let's see how the long shunt motor. The long shunt motor. For example, this is series. Now I want long shunt. That's why I have to connect here. So this is my long shunt motor. Motor nothing but it should supply the current. The supply. It will take the current. This is ISE. And this is my armature current. And this is my shunt field current. And this is my armature resistance. Armature resistance. And this is my back EMF. And this is my back EMF. Right? So this is my cumulative compound motor. Right? Now what they given? Motor is driving at load, rated torque and rated speed. The load, the rated torque, it is having rated torque and rated speed. rated torque and rated speed. Right? Next. Now, if the series field is shunted by a resistance, actually, this field winding having some resistance RSE, actually. But now what they given that if the series field is shunted by resistance R, this is shunted by resistance R, this is shunted by resistance R. Its value some resistance R, shunted by resistance R. Now tell me, shunted by resistance R equal to RSE, keeping the torque constant. They given that the torque is constant. They given that the torque is constant. Now tell me what happened to armature current. Actually, the question. Once see here, actually, when this is not there, the total ISE flowing through this winding. When this is not there, the total series field current flowing through this winding, which produces some flux. But when this is connected in parallel to this one, the series field current is divided into two halves because these two resistances are equal. They given that these two resistances are equal. When these two are equal, the series field current divided into two halves. Nothing but here half of the series field current, here half of the series field current. Nothing but the series field flux reduced to half. The series field flux reduced to half. Yes or no? Because the current flowing through this winding is half. That's why the series field flux reduced to half. Generally, we know the torque is directly proportional to phi into Ia, right? Torque is directly proportional to phi into Ia. And generally here, the flux reduces. Generally here, the flux reduces. But the torque should be constant. To maintain the constant torque, what about armature current? To maintain the constant torque, the armature current should be increased. Yes or no? When flux reduces, the armature current should be increased. So, to maintain the constant torque, the armature or simply the DC motor draws more armature current. To compensate this low torque, the motor draws more armature current. That's why our answer is armature current increases. When the resistance in parallel to RSE connected, the flux reduces to half actually, and then flux reduces, so nothing but the armature current increases. The motor draws more armature current. This is our answer, armature current increases. Okay, what they given? A differentially compound DC motor, right? Let's see how it is. Differentially compound DC motor. They given simply differentially compound DC motor, right? Let's take a long shunt motor. Let's take a long shunt motor. Let's take a long shunt motor. Right? This is my long shunt motor. Motor nothing but it should take the supply. Now, this is my long shunt motor. How we can decide is it is differentially compound or cumulative compound? Simply the flux phi is equals to, simply the flux phi is equals to phi sh differentially compound minus phi se. Now this is my differentially compound motor actually. Differentially compound motor, differentially compound motor, that's why EB, back EMF. And generally motor produces a electromechanical torque, right? Electromechanical torque or electromagnetic torque. And the speed is also in the same direction actually. It is going on like this. It is doing like this. Now tell me what they given. A differentially compound DC motor with interpoles and with brushes on the neutral axis. Generally interpoles on the neutral axis only. And in generally brushes placed along the neutral axis, magnetically neutral axis, MNA, right? Placed along the neutral axis is to be driven as a generator. Is to be driven as a generator in the direction with the same polarity. In the same direction with the same polarity. This motor should be driven as a generator in the same direction with the same polarity. In the same direction, nothing but the torque also should be in the same direction. The torque also should be in the same direction. In the direction, the generator in the direction with the same polarity of the terminal voltage won't change this terminal voltage. Now tell me, generally, if it is act as a generator nothing but the armature current should be in this direction. The armature current is in this direction. And ISE is in this direction. ISE in this direction. Right? Yes or no? And next one, the ISH in the same direction only. There is no any change of ISH. But ISE changed and armature current also changed. Now this is my generator. Which generator? A long shunt generator, of course. Yeah, we know that long shunt generator. But it is differential compound generator or cumulative compound generator is my question. Tell me, it is differential compound or cumulative compound? See here, when the phi SE change, nothing but this minus comes to plus. Now see here, phi is equals to phi SH plus phi SE. Nothing but this is the flux for cumulative, right? That's why now this is a cumulative compound generator. Now this is a cumulative compound generator. Cumulative compound generator. Now this is a cumulative compound generator, right? And actually here, see here, the flux is positive only. Flux is positive only. We know that torque is directly proportional to phi into Ia. The flux is positive only, but armature current reversed. Armature current reversed. When armature current reversed, torque also reversed. Torque also reversed. Nothing but this electromechanical or electromagnetic torque is in this direction. Yeah, of course, in generator, generally in generator, the electromagnetic torque and speeds should be in opposite to each other, right? In motor, those two should be in the same direction. But in generator, those two should be in opposite direction. Yeah, of course, the rotor rotates in the same direction and the machine acts as a cumulative compound generator. Is there any requirement to change the interpoles? No need to change the interpoles polarity. Because we already got that it is a cumulative compound generator and which rotates in the same direction. And it is developing the same power, same direction and same polarity. Same polarity. There is no change in plus or minuses. This is now EG, generated EMF. So our answer is, it is act as a cumulative compound generator without changing polarity of interpoles. Without changing polarity of interpoles. Here actually we should observe this phi SE. When phi SE is reversed, that's why it is plus. Now this is cumulative compound generator, that's it. Right? Okay, next question. A 4-pole dynamo, nothing but generator. A 4-pole generator with a wave wound. Its armature winding having the wave winding. Has 51 slots. 51 slots containing 20 conductors in each slot. 51 slots containing 20 conductors in each slot. The induced EMF is 357 volts. They given induced EMF also. And the speed is 8500 RPM. And the speed is 8500 RPM. The flux per pole will be dash. So they ask that flux per pole. Generally, what is the formula, sir? Generally, the generated EMF EZ is equals to phi Zn by 60 into P by A. This is generally our formula. Now tell me, what is the flux they given? we have to find out the flux. And tell me, how many conductors are there? They given that 51 slots containing 20 conductors in each slot. 51 slots, each 20 conductors. Each 20 conductors. Then what is the answer? 20 into 51. 20 into 51. Nothing but 20 into 51. We have to calculate 20 into 51. Nothing but 1020. Yes or no? 1020 number of conductors. Now tell me, what is n? The speed they given 8500 rpm. Of course, generated EMF also they given generated EMF 357 volts. Then tell me, for wave winding, how many number of parallel paths are there? For wave winding, number of parallel paths are 2. Yes? And next one, here they given number of poles are 4. Now tell me the answer. Now, the generated EMF they given, generated EMF 357 volts. And flux per pole we have to find. And number of conductors they given 1020. Right? And next the speed they given 8500 divided by 60. And number of poles they given 4 and parallel paths 2. Then calculate the flux per pole. If you calculate the flux per pole, if you simplify this one, you can get 1.235 milliwebers. 1.235 milliwebers. Nothing but, according to our options, which are the following is correct answer? Which are the following is suitable answer? 1.235, they given simply 1.2 milliwebers. 1.2 milliwebers. Right? So, this is our answer. Very simple question. Based on the basic formula, generated EMF. The speed characteristics, the torque speed characteristics of repulsion motor coincide with which of the following motor? Generally, first you have to know about repulsion motor. Actually, I explained in induction machine. Actually, you have to know about repulsion motor first of all. And here my question is that the repulsion motor torque speed characteristics are similar too. Generally, the repulsion motor which used for high starting torque and variable speed. Tell me, in which of the following case, which motor is used for high starting torque and variable speed applications? Yeah, exactly. The DC series motor used for high starting torque and variable speed applications. That's why the torque speed characteristics of repulsion motor is coincides with the DC series motor. The torque speed characteristics of repulsion motor are similar to the torque speed characteristics of DC series motor. This is a question. Yeah, let's see next question. A 200 volts, 10 kilowatts, lap wound. A lap wound DC generator has 10 poles and 500 conductors. 10 poles and 500 conductors. 10 poles and 500 conductors on its armature. If the pole face covers 80% of pole pitch, what he said, for example, if my motor is like this, for example, this is my pole face, this is my pole face, the pole face covers 80% of pole pitch. Pole pitch nothing but actually the distance between two adjacent poles. In this pole pitch, 80% of pole pitch is only the pole face. Right, 80% of pole pitch. The pole face conductors required to compensate. The pole face conductors required to fully compensate for armature reaction. Generally, to compensate the armature reaction, here we are using the compensating winding. here we are using the compensating winding actually, the compensating winding, right? So they asked that the conductors required to fully compensation. Actually, they given that the pole phase is equals to 80% of pole pitch. 80% of pole pitch. Pole phase is equals to 80% of pole pitch. Now tell me, actually per a pole pitch, how many number of conductors? The conductors are there per pole. The conductors per pole is equals to Z by P, the conductors per pole, Z by P per parallel path. So actually the conductors per pole value Z by A into P. Z by A into P, actually the conductors per pole for full pitch. But here we require to calculate pole phase conductors. So the conductors per pole for pole phase is equals to, for pole phase the conductors per pole is equals to 80% of pole pitch, right? 80% nothing but 80%. Cent nothing but 100. 80% of Z by A into P. 80% of Z by A into P. Let's calculate this value. 80 by 100 into number of conductors are 500 divided by how many parallel paths are there? Actually, this is a lap winding, right? This is a lap winding, right? So lap winding nothing but number of parallel paths is equals to number of poles. Number of parallel paths is equals to number of poles. How many poles are there? 10 poles are there, right? So 10 into 10. Number of parallel paths also 10 and number of poles also 10. So 10 poles, that's why. So now tell me what is answer? These two gets cancelled. These two gets cancelled. Then what is answer? What is answer actually? 400 by 100. So the actual answer is 4. The actual answer is 4. Right? Are you getting or not? So actually the answer is 4. This is only 100% correct answer. This is only 100% correct answer. Based on our formula, the pole phase conductors per pole is equals to 80% of actual value. What is 80%? Nothing but 80 by 100 or simply 0.8 also you can write. And number of conductors are 500 they given. And then after number of parallel paths are 10, number of poles are 10, then we can get the answer 4. A 240 volts DC shunt motor, armature resistance is 0.5 ohms. Armature resistance they given. Has a full load armature current, simply. Has a full load armature current of 40 amperes. Full load current they given 40 amperes. Find the ratio of stalling torque to the full load torque. Find the ratio of stalling torque to the full load torque when a resistance of 1 ohms, when a extra resistance of 1 ohms added or connected in series with the armature. Added in series with the armature or connected in series with the armature. This is generally the question. Right? Let's tell me what is the answer here. Generally DC shunt motor they given. And we have to find stalling torque to the full load torque. Stalling torque to the full load torque. Generally we know that the torque is directly proportional to Ia. Torque is directly proportional to Ia. We have to find out Ia here. We have to find out Ia and the current at the stalling torque to the and full load armature current is our answer actually. Let's see however. Let's see. First you have to know what is stalling torque. What is stalling torque? the torque at speed is equals to 0 is called as stalling torque. Stalling torque nothing but the torque at speed is equals to 0. The torque developed by the motor when the speed reached to 0 is called stalling torque. When speed is equals to 0, the back EMF is also 0, right? When speed is equals to 0, back EMF also 0, right? If back EMF 0, then generally V is equals to EB minus IARA when V is equals to EB minus IARA, but here EB is 0. So V they given 240 is equals to IA into RA. RA they given. What is the value of RA? 0.5. 0.5. RA they given 0.5, and actually here 1 ohm resistance added. 1 ohm resistance added in series to the armature, right? So plus 1. Right? Now find out IA. Tell me, IA is equals to 240 divided by 1.5. Can you tell me what is the value? Let's calculate it. 240 divided by 1.5, nothing but 240 divided by 15 divided by 10, nothing but 10. So let's calculate. 5 2s are 5 3s are, right? 3 1s 3 8s are. So my armature current at stalling torque is 160 amperes. Actually, it is a DC shunt motor. The armature resistance 0.5 ohms only. But he is trying to control the speed. Yes or no? The armature resistance control method. In armature resistance control method, we can reduce the speed. Actually, he added 1 ohms resistance in series to the armature. In armature resistance control method, when this 1 ohms added to the machine, the speed comes to 0. When that 1 ohm added in the circuit, then the speed comes to 0. That at that condition, the torque is called a stalling torque. At that condition, my armature current is 160 amperes. And generally we know the torque is directly proportional to IA. So now I want the stalling torque to the full load torque ratio, nothing but the armature current at stalling torque 160 and the armature current at full load. Armature current at full load 40 amperes, they given 40 amperes. So my answer is 4. My answer is 4. Stalling torque to the full load torque ratio 4. Here we have to know stalling torque nothing but the torque developed by the motor when speed equals 0. Right? This is our question. A 4-pole lap-wound DC generator. 4-pole lap-wound DC generator. Now tell me, for lap winding, how many brushes we are using? For lap winding, number of brushes is equals to number of poles. For lap winding, parallel paths is equals to number of poles. For lap winding, number of brushes is equals to number of poles, and number of parallel paths is equals to number of poles. Generator has a developed power of P watts, and voltage of E volts. Power P and voltage E. In this number of parallel paths, brushes are number of poles, nothing but 4, right? What he said, 2 adjacent brushes of the machine are removed. Out of 4, 2 brushes are removed. Out of 4, 2 brushes are removed as they are worn out. They are completely damaged actually. If the machine operates with remaining brushes, remaining nothing but out of 4, 2 damaged, nothing but we have again 2 brushes. Remaining 2 brushes. The developed voltage and power that can be obtained from the machine are. Yeah, let's take it once. Actually, the diagram for that, actually we should have 4 brushes. because this is a 4-pole lap winding machine. For example, this is brush 1 and this is my second brush, and for example this is my third brush, and for example this is my fourth brush. These are my 4 brushes. Of course, again we have a 4 parallel paths, right? This is my first parallel path, this is my second parallel path, and this is my third parallel path, and this is my fourth parallel path. In generally in DC machine, if one brush is positive, the adjacent brush should be negative. If one is negative, adjacent positive. If one is positive, adjacent negative. These are 4 brushes and 4 parallel paths. In generally, the current flows like this: negative brush to the positive brush, negative brush to the positive brush, negative brush to the positive brush. These 2 positive brushes combinedly gives us the positive terminal, and these remaining 2 negative brushes combinedly gives us negative terminal, which is our DC. Positive and negative terminals. Positive and negative terminals. This is our DC. Now what he said here, in this out of 4 brushes, 2 brushes are damaged. 2 brushes are damaged. For example, my brush 1 damaged and brush 2 damaged. For example, brush 1, brush 2 both are damaged. Then this parallel path also open circuited, and this parallel path also open circuited, and this parallel path also open circuited. Because this brush damaged, right? There is no current. And this brush and this brush both are damaged, right? Then there is no current and there is no current. Nothing but we have only current in this parallel path. We have only current in this parallel path. Now tell me, now the armature current is equals to, how many parallel paths are there? Only one parallel path is there. Only one parallel path, nothing but the total current divided by 4. Actually, 4 parallel paths are there. For example, total current is I. The current in each parallel path is I by 4. The current in each parallel path is I by 4. The current in each parallel path is I by 4. I by 4 plus I by 4 plus I by 4 plus I by 4, nothing but I, right? Otherwise, you can calculate the armature current. See, how many parallel paths are active? 1 parallel path is active out of 4 parallel paths. 1 parallel path is inactive out of 4 parallel paths. 1 by 4th of the total current. Otherwise, you can calculate simply the current for each parallel path is I by 4. Whatever, my armature current is I by 4. What is the EMF? Generally, these all are in parallel, right? Even though remaining 3 parallel paths are damaged, there is no change in EMF. The EMF is same. The generated EMF is E only. The armature current is I by 4 only. Now tell me, what is power developed by the machine? The power developed by the machine is equals to E into I, right? So E into I by 4, finally P by 4. The armature current is I by 4 and the generated EMF is E and the power developed is P by 4. Very simple question. Here, when 2 adjacent brushes are damaged, the developed power in the machine is just 25%. 1 by 4, nothing but just 25%. This is about the question. Alright, next question, match the following. Match the following. So tell me, sir, no load and block rotor test. Generally, where we connected this no load and block rotor test? Is on DC machine? Is on synchronous machine? No. So, the no load and block rotor tests are conducted on induction machine. Right? So, you have to know actually what is no load test and what is block rotor test. Generally, in no load test, we can find out the no load losses of the machine. In block rotor test, we can find out the copper losses of the machine. Right? So, generally, the no load and block rotor tests are conducted on induction machine. And next one, Sampana's test. Tell me, Sampana's test conducted on which of the following? Sampana's test conducted on the transformer. Do you know what is Sampana's test? The Sampana's test is also called as Hopkinson's test, back-to-back test. It is also called as combination of OC and SC test. It is also called indirect test. You have to know about Sampana's test actually. Right? Then after Swinburne test. So tell me, Swinburne test conducted on DC machine. Swinburne test is a no-load test of the DC machine. One of the no-load test of the DC machine. Actually, we have to know all this about, first of all, if you buy Saimeda video classes, you can find all those in the corresponding machines. In test, for example, DC machine. Generally in DC machine, tests are two types. One is the no-load test, one is the load test. No-load test nothing but like a Swinburne test and a retardation test. And load test nothing but Hopkinson's test and field test. Field test, the only test which conducted on series motor. Very, very important. So if you buy Saimeda video classes, you can find all the tests corresponding to the machines. It is useful for any competitive exams, right? So generally these are about the question. We can easily. Can you tell me what are the tests in synchronous machine? Can you tell me what are the tests in synchronous machine? In synchronous machine, we have a slip test. Yeah? Do you know what is slip test? To find out XD and XQ. To find out XD and XQ, we conducted slip test. Of course, here we have a OC also. It is called as open circuit characteristics, OC test. Of course, we are conducted SC test also, short circuit characteristics. OC test, SC test, slip test. We have a 3 tests in synchronous machine. Right? So, this is about the question.